So you are welcome. Today our discussion is on electric potential and potential energy. When we talk about electric potential energy is the work done to move a charge from a point in an electric field of a charge which has low intensity to another point which has great or high intensity in the field. So the work done equals the difference between the electric potential energy of these 2 points in the field. So if you look at this diagram, we are having a charge of Q naught, and at point A in the diagram we can see that the intensity of the field at point A is low and that of point B is high. So by moving the charge from point A to point B, which has a greater intensity, there will be a work done, and that work done gives the electric potential energy. So the electric force is a consecutive force. Therefore, the path along which the charge is moved from point A to point B has no influence. So there's no path to be considered here when you are moving the charge from point A to point B, since the force is a consecutive force. So the work done is therefore giving us work equals the electric potential energy at point B minus electric potential energy at point A. So we find the difference between the potential energies between these 2 points. So electric potential energy is the same principle applied in gravitational electric field or gravitational potential energy. So if you look at this diagram, moving an object at a height that is working against gravitational energy or gravitational force, there will be a work done. So if you look at this diagram, you're moving the ball from point A to point B. Point A has a shorter height and point B has a higher height, meaning at point B the gravitational force will be higher compared to point A. So it's the same principle from electric potential energy that is applied in the gravitational potential energy. So the work done in gravitational potential energy is the gravitational potential energy at point B minus potential energy at point A. And with this, the potential energy for the gravitation is the mass times gravity times height. So we consider the mass of the object, the gravitational constant, and the height at which we move the object against the gravitational force. So since the ball is moved from rest to rest, the kinetic energy for both points will be 0. So at point A, the ball was at rest, and we moved it to point B, and it went to rest as well. So there will be no kinetic energy considered here. Now, gravitational potential energy take into consideration masses, and electric potential energy take into consideration charges. So if we look at this diagram, in the gravitational field, there are masses that are moved from one point to another point with a difference in the gravitational energy. And for electric field or electrical potential energy, there are charges that are moved from point A to point B. So we take note of these two. Now, when a positive test charge is moved against the direction of an electric field, it is similar to moving the mass upwards within the Earth's gravitational field. So as I said earlier on, when you move a test charge against the direction of the electric field, meaning work will be done, you need much energy. So moving the charge against the direction of the electric field, an external force is needed. Since you are working against the field, it is similar to moving the mass upwards in the gravitational field. You are working against the gravitational force, so much for external force is needed to get this work done. Both movements are like moving against nature, and work is required by an external force which tends to increase the potential energy of the charge. So moving the charge against the electric field and moving a mass against the gravitational field, an external force is needed to make this work, and therefore increasing the potential energy for the mass as well as the charge. So when the movement is in the direction of the field, less energy is required, hence decreasing the potential energy of the charge. So if we are moving the charge in the direction of the electric field, less work is required. And if we are moving a mass in the direction of the gravitational field, less work is required. Therefore, the potential energy for this scenario will be less compared to moving against the direction of the field. Now, work done in moving the charge from point A to point B depends on the magnitude of the charge. So, to get to the work done, the magnitude of the charge is very important. Therefore, the electric potential energy per unit charge gives the electric potential. So, the electric potential equals the work done over the test charge or the unit charge. That is the electric potential. And we know that the work done is the electric potential energy at point P minus the electric potential energy at point A. So we now have a new equation, which is electric potential equals the work done over the test charge. And with this, the potential depends on the magnitude of the charge. Now, the electric potential difference between 2 points. So finding the potential difference between 2 points is find the difference for the potential at point B and point A. That is our electric potential energy at point B minus electric potential energy at point A all over Q naught will be equal to potential at point B minus potential at point A. And this will give us the difference between the potential in the 2 points. Now, electric potential is the work done moving a test charge from infinity to a point in the electric field at a distance r from the charge. So if you look at this diagram, at infinity, the potential energy is assumed to be 0. At infinity, the potential energy is assumed to be 0. So the work done in moving the test charge from infinity to a point at a distance r from the charge gives the electric potential. So at that point here, the potential will not be equal to 0 since it is at a distance r from the charge. So the test charge is moved with a negligible acceleration to avoid producing kinetic energy. So when we are moving the electric charge from infinity to the point, it is moved in such a way that kinetic energy will not be recorded or kinetic energy will not be noticed from the movement. So it is moved with a negligible acceleration. Now the potential at a distance r due to a point charge is given by V equals kq over r. So the potential is therefore the constant k times the charge over the distance r. And from this expression, we can assume that the potential at an infinite distance is 0. So as I said earlier on, the potential at r equals infinity is 0. So moving the charge from that infinite point to point P will give us a potential V. And the potential can be negative and positive considering the unit of the charge. So as I said, the magnitude of the charge is very important in potential. The magnitude of the charge is very important in electric potential. So when the charge is positive, the potential is positive. so as the charge being negative, giving a negative potential. So as I said that earlier on, the sign of the charge affects the sign of the potential. So if it is positive, the potential will be positive, and if it is negative, the electric potential will be negative. So as you can see in the diagram here, the charge was positive, giving a positive potential, and here the charge is negative, giving a negative potential. So the sign of the charge affects the potential. Now we will talk about electron volt. Electron volt is the measure of the amount of kinetic energy gained by an electron when it accelerates through a potential difference of 1 volt. So it is the measure of the amount of kinetic energy. So with this one, we are measuring the kinetic energy of the charge when we move the charge from one point in the electric field to another. So that amount of kinetic energy gives the electron volt. And with this, the voltage or the potential difference in that field is supposed to be 1 volt to give us 1 electron volt. That is how come we got electron volt. So electron volt is the measure of the amount of kinetic energy gained by an electron when it is accelerated through a potential difference of 1 volt. Now it is the change in potential energy of an electron when it is moved through a potential difference of 1 volt. So electron volt can be the change in potential energy. Electron volt can be the change in potential energy of an electron. So with this one, we consider the movement of the charge. That is why we are getting the amount of kinetic energy. So we consider the acceleration, the movement, the acceleration of the charge through the potential difference. And the potential difference is supposed to be 1 volt. And it is also the work done in moving an electron through an electric potential difference of 1 volt. So it is a work done. So doing work needs a movement from one point to another. And with that movement between the electric potential of 1 volt gives the electron volt. So 1 electron volt equals 1.6 times 10 to the power minus 19 joules. So it is a unit for work done, and it is a unit for kinetic energy as well. And its conversion is 1.60 times 10 to the power minus 19 joules for 1 electron volt. So we take note of that. So when we move an electron from the negative plate to the positive plate, and the potential difference between the plate is 1 volt, that acceleration or that movement and the existence of kinetic energy gives the electron volt. So we take note of that. Now, electric potential due to many charges. So the electric potential at any point in space produced by any number of point charges can be calculated from the point charge expression by simple addition. Since the electric potential is a scalar quantity, so as we saw earlier, that potential equals KQ over R. So when we have many point charges, we can find the electric potential at a point due to these charges by simply adding them up. So what will be done is, when we are having 3 charges, Q1, Q2, Q3, with their radius respectively R1, R2, and R3, the potential at a point due to these charges can be determined as V equals KQ1 over R1 plus KQ2 over R2 plus KQ3 over R3. So this is the expression for finding the potential at a point due to many charges. So it is just simple addition. We add all their potentials up to give the potential at that point. Now, the electric potential between plates. Electric potential between 2 plates. It is giving us the work done over the charge where A is a point on the negative plate with lower potential and B is a point on the positive plate with a higher potential. So the electric potential between plates, we are moving a charge from the negative plate to a positive plate, and the negative plate has lower potential and the positive plate has high potential, as we've noticed earlier on. Now the work done to move this charge from point A to B is giving us force times the change in distance. The work done is force times the change in distance, and then now this change in distance is the movement from point A to point B. So the force required to move the charge from point A to point B and the distance between point A and B gives the work done. But we've seen earlier on that electric force equals charge times electric field. So when we multiply the charge by the electric field, it will give us electric force. Therefore, doing that substitution into the work done, we are getting work done to be equal to charge times electric field times change in distance, as we can see here. So the work done equals Q naught E times change in distance. Therefore, doing that substitution again into the potential difference between the plates, we are having the potential difference to be equal to Q naught E change in D over Q naught. That is, we substituted the work done into the potential difference equation. So after substitution, Q naught will cancel out Q naught, leaving the potential difference to be equal to E times change in D, leaving the potential to be equal to E times change in D. Therefore, our electric field can be calculated as change in potential between the plates all over change in distance. So this expression can be used to find our electric field, and this expression can be used to find the potential difference between the plates, the electric potential between the plates. So looking at this diagram, here is point A, here is point B. The electric field direction is moving towards point A, and point A has a lower potential compared to point B. So when we are moving the charge from point A to point B, an external force is needed, therefore increasing the potential. So the work done for this charge to move from point A to point B is the charge times the electric field times the change in distance. And the potential difference between the plate is the electric field times the change in distance. So we take note of that too. Now let's look at some worked examples. So the work done to move a test charge Q naught, which equals plus 2 times 10 to the power minus 6 coulomb at a steady speed from point A to B is 5 times 10 to the power minus 5 joules. Find the difference in the electric potential energies of the charge between the 2 points, and then determine the potential difference between the 2 points. So looking at our solution, the first thing we will do is note out all our given parameters in the question. So you write our charge, then write our work done. Now what we are asked to find is the difference in the electric potential energies. And we know that the difference in the electric potential energy is the work done. That is, work done equals the electric potential energy at point B minus potential energy at point A. Therefore, the work done will be equal to the difference in the electric potential energies, which equals 5 times 10 to the power minus 5 joules. So over here, it will be just direct equation. We equate the work done to the difference in the electric potential energy, which will be equal to 5 times 10 to the power minus 5 joules. Now the difference in the potential between the 2 points is giving us the work done over the charge. Now we know the work done to be equal to electric potential energy at point B minus the electric potential energy at point A. Therefore, we do our substitutions, and we're having 5 times 10 to the power minus 5 all over 2 times 10 to the power minus 6. So the numerator is the work done or the difference in the electric potential energies, and the denominator is the charge. So after computing, we are having the difference in potential to be equal to 25 volts. We are having the difference in the potential to be equal to 25 volts. Now, the next question. Using a zero reference potential at infinity, find the potential due to a point charge of 2.9 times 10 to the power minus 9 coulomb at a distance 2.3 meters away when the charge is A positive and B negative. So we are finding the potential, and in the solution we first state out our equation for potential, which is V equals KQ over R. Then write out our parameters. So Q equals 2.9 times 10 to the power minus 9. Our R is 2.3 meters. And we know our K constant to be 8.99 times 10 to the power 9. So for the first part, when the charge is positive, we're having potential to be equal to 11.34 volts after substitution and computing. So when we substitute the parameters into the equation, we have our K, our Q, and our R. We're having V to be equal to 11.34 volts. And when the charge is negative, we're having V to be equal to minus 11.34 volts. So as I said earlier on, the sign of the charge affects the potential. So when it is positive, the potential is positive. And when it is negative, the potential is negative. So we take key note of that. Now, our next question is, how much work is done by the electric field in moving a minus 7.7 microcoulomb charge from the ground to a point whose potential is 55 volts higher? So we want to find the work done in moving the charge through a potential. And we know that potential equals work done over charge. So in the solution, we make our work done the subject. Given potential times charge. Therefore, substituting our parameters into the equation, we have work done to be equal to 55 times minus 7.7 times 10 to the power minus 6. So micro is times 10 to the power minus 6. After substituting our values, we're having the work done to be equal to 4.24 times 10 to the power minus 4. So with work done, we don't consider the sign of the charge as compared to potential. So we exclude the sign of the charge when computing for the work done. So therefore, our work done will be equal to 4.24 times 10 to the power minus 4 joules. So this is the work done by moving a charge through the electric field of potential 55 volts. Now here are some questions that you can try your hands on.